People, we have a quiz next Wednesday in class, closed book. Okay, there's a quiz announcement that was distributed and is on the website that tells you all the facts you need to know about it. Okay, it'll be held in this room. I'm sorry, this is the best we were able to obtain under the circumstances for taking quizzes, but that's what we've got. Monday, remember, is a holiday. I'm sure very few people have forgotten that. Okay, and respond to the final survey if you want for when we are going to hold our final, okay, to indicate conflicts. Okay, the quiz is essentially made up at this point. I think it's a good quiz. It covers the important topics. It's very basic material, pretty much very little innovation required on this quiz. Okay, mostly it's a quiz of do you understand the issues in the analysis of algorithms as we've studied it up to this point. So solving recurrences, understanding divide and conquer, analyses with indicator random variables, topics from the overall that we've covered in the terms. So I don't think that there's anything that requires a tremendous amount of imagination. The imagination is quiz 2. Okay, so this one is basically so that people know whether or not they should continue in the course, and is usually a good indicator as to whether you're going to pass the course. Okay, it's not a good indicator whether you're going to get an A or a B. It might indicate whether you get a B or a C, but it may not indicate. Sorry, it probably indicates whether you get a C or an A in the class, but it won't indicate whether you get a B or a C or an A or a B. Okay, so I think it's a good exam. Okay, I think there's enough. You'll have enough time to do it, and there are 5 problems on it. But one of the problems is one of the true, false, and justify things with a lot of small parts. Okay, and some recurrent solving, and then some more in-depth problems. So I encourage you to do the practice quiz that we put up on the website. And we put up 2 versions of it, one with solutions and one without, so that you can, if you want, test yourself in an 80-minute period, because that's how much you'll have for this exam, okay, to see how well you do. The last quiz actually has some problems. I think the practice quiz that are topics we didn't cover this time, like sorting networks. We're not covering sorting networks, so you don't have to know that. In recitation, we'll hand out on Friday, where they do the quiz review, they'll hand out a list of topics, just so that you can check off. Have you studied each of those topics and know the key issues? Okay. Last time we talked about hashing. Hashing is one of the all-time powerful programming methods, okay? Really powerful, used all over the place, okay? A zillion ways to innovate in hashing, and it's got a main weakness. And what is the main weakness of hashing? What's the problem with hashing? Excuse me? Collisions, yeah, but we found ways you could resolve collisions. No, it actually takes space only proportional to the number of items you're putting in the table. Pretty good, too. What's the weakness of hashing? Yeah?
Maybe it has because of regularity or maybe have passing of data sometimes, and we want to distribute it as randomly as possible.
Yeah, that is basically no matter what hash function I pick, there's always a set of keys that's going to be bad for that hash function. Okay? For any choice of hash function, okay, there exists a bad set of keys that all hash to the same slot. Okay? So one way to think about this is as a situation where you have an adversary. Okay? And let's say that you're both vendors providing service to a company, and the service you're providing is a compiler. Okay? And you want to argue not only that your compiler produces good code, but that it runs fast. And so you've implemented your symbol table using the fastest methods you know. And when you get a keyword, such as for or if, or any of the other words, or the program variables, you store those in a hash table. Okay? And so what often happens in competitions is you're allowed to provide inputs that will go to your opponent's code. Okay? So you can provide your own code, and then they're going to test these two compilers against each other, and you're allowed to provide inputs. He's allowed to provide inputs that'll be input to your code. In this case, the input is a program with a bunch of identifiers, variable names, and so forth. So, what will if you're a good adversary, what are you going to do? What are you going to do? Spread the wealth here, the contact wealth. Got a small class today, which is really nice. Okay? So what would you do? Okay? I mean, you get to see his code. Yeah. Well, you're trying to beat him, right? So before you worry about your code, you're going to produce a bad set for him, right? Okay? So how are you going to produce a bad set? What will you do?
Analyze his algorithm.
Yeah. Yeah, analyze his algorithm, see what his hash function is, and find a bunch of identifiers that all hash to the same slot. Okay, and then when he runs his code against yours, his will be really slow. Okay? Whereas yours, okay, you'll make it so that your hash function runs really fast on those inputs. But what's he going to do? Okay, he's going to do the same thing. Okay? He's going to do the same thing. So you want some advantage over him if he's merely a good programmer and not an excellent programmer. Okay? You want some way of defeating him. And that method is what we just heard a minute ago, which is use randomization. Okay? So the idea is that we'd like to do is to choose a hash function at random. Independently from the keys. So for example, you can imagine that your code has two hash functions. And you flip a coin at runtime to see which one you're going to use. Now his job is a lot harder. Or her job. Okay? A lot harder. Okay? Why? Because now she's got to find something that will be bad for both hash functions. That's harder. Okay? That's harder. But is it that much harder? Well, you run a bunch of experiments and you find a bunch of things that hash to the same bucket under both schemes. Okay? Well, you could do 3 hash functions. Okay? And you could play a game, and probably from a practical point of view, you could pick a bunch of hash functions from a practical point of view, which would be sufficient to cover the space, but you wouldn't necessarily know that your adversary out there wasn't smarter than you and would be able to come up with a way of defeating any particular collection you took. And that brings us to the topic for half of today's lecture, which is universal hashing, which is a way of picking a set of hash functions. So if you pick a random one, you're guaranteed with good probability that it's going to hash any set very well, an arbitrary set. Okay? And so we now have sort of the solid basis of mathematics to say Well, the other guy could get lucky because I could pick a bad hash function, but that's the only thing he can do. He has no control. The adversary has no control, okay, on whether I have a good hash experience when I run my program or not. Now, where have we seen an argument like this before? Yeah. Randomized quicksort. Okay, same type of argument. And it's one of the advantages of a randomized algorithm is that nobody can pick a set of inputs that's going to elicit a bad response from your program. Okay? Your program behavior is only dependent essentially on the random numbers you pick. And you could be unlucky, but then you can use your probability techniques to bound the probability that you're unlucky. Okay? And you make the probability really small, like the probability, say, that all the gas in this room just happens to rush out that door. Okay? Because the Brownian motion just takes it. Okay? So you can work with probabilities, probably not that are quite that small. Okay? That's really small probability. But probabilities that sort of make things behave like they're gases. Okay? And the nice thing about, we don't do too much high probability analysis in this. We concentrate mostly on expectation in this class. But one of the nice areas of theoretical computer science is high probability analysis. Because literally there, just like, when you studied gases originally, they didn't tell you that there was all this Brownian motion there. They said there were things like temperature and pressure and volume, right? And they said if you have an ideal gas, then you change these parameters and they obey somebody's law who I forget because that was way longer ago than I had this stuff than you folks have, okay? Okay, and they treated it as if it was a deterministic system, even though gases are in fact a stochastic system, okay? Well, the kinds of things we can do with probability in algorithms with high probability analyses are very similar. You can make it so that the statistical behavior of your program is so regular as to almost be deterministic. Okay? That's really quite amazing. Okay? Just by bounding the probability. And your adversary, if there is one, who's providing you inputs, has no control. Okay? It's all just this question of doing the analysis. So universal hashing is one such technique. So let's define what a universal set of universal hash functions is. So let's let U be a universe of keys. And let script H be a finite collection of hash functions mapping U to the set 0, 1 to m minus 1. This is a set of hash functions. Okay? And they're all hashing into something that's going to end up being our table slots. Okay, so we're looking at simple hash functions here, not the ones that have probe sequences and so forth. Okay? So we say H, okay, is universal, okay, if for x and y in U, where x is not equal to y, so they're distinct values, the size of the set h and h such that h of x is equal to h of y is equal to size of h over m. Okay, so what does this definition say? Okay, so this definition essentially says that if I pick two particular keys, okay, so these are the things, the two particular keys might be something your adversary picks. Okay? picks two different keys, then if you pick a hash function in H at random, okay, then the number of hash functions in H, okay, so how many hash functions are in H? That's this here. So if you pick one at random, then the chances that it collides, that h of x and h of y collide, okay, is just 1 over m. Okay? So this is saying that the number, the total fraction of hash functions on which it collide is 1/mth of the total number. And so if you pick one at random, okay, it'll be just probability of 1 over m that they collide. That's pretty good, okay? Because that's the type of property we would like, is that the chances that two keys collide in a hash table of size m should be 1 over m. That's what we use when we use either the uniform hashing or the simple uniform hashing assumptions. Okay? So just to rewrite that, the chance of collision between x and y is 1 over m if h is chosen randomly from H. Okay, so I hope people can read the mathematics here, okay? Because if you can't read set notation, you're going to have a hard time on this upcoming exam. Okay, so let's just do a picture of that just to make it really clear. I like to belabor basic points because if people miss the basic points, they're not going to understand any of the math that I get to. Okay, so here's my set H of functions. Okay, and there's some set here, and I'll shove them all over to the left-hand side here, which is this set here, the set of H such that H of x is equal to H of y. So that's that set there. Okay? So that's the set for which these two things collide. And if I look at this as a fraction, if I push them all over here and they're also lined up nicely and so forth, then this fraction is just 1/mth times the size of H. Okay? And the whole thing, of course, is the size of H. Okay? So therefore, if I close my eyes and throw a dart, the chances that x and y will collide is 1 over m. Okay? Throw my eyes, throw a dart, pick a hash function. Okay, so this is a neat idea to pick the hash function at random. Okay? Now, suppose that we choose, so what I want to do is show that this actually does give us a good hash function when we're actually hashing a bunch of keys. This intuitively gives you a good hash function, but let's prove that. Okay? So let me just write the theorem over here. So suppose we choose H randomly from H, capital script H. Okay? And suppose we wish to hash n keys into m slots in table T. Okay? So the theorem says then for a given key x, the expected number of collisions with x is less than n over m. Okay? So if I pick a key x, then the expected number of collisions I'll get with that key is n over m. And what's this value? What do we call this value? Load factor, good. Load factor. That's the load factor, which is the average number of keys per slot. So this is a good theorem. Okay? This is a good theorem. So I'm not going to get a large number of things to do it. So therefore, for example, if I pick a hash table where the number of slots is proportional to n, okay, then the expected number of collisions will be constant, which is what we'd like, okay, because that's generally how you pick a hash table so that you can get the search time way down. Okay? Okay, let's prove that theorem. So let's let capital C sub x be the random variable denoting the total number of collisions of keys in T with x. And let little c sub xy be an indicator random variable, which is 1 if h of x is equal to h of y, and 0 otherwise. Okay? So let's make a couple of observations here about these two random variables. What's the expectation of cxy? Yeah. 1 over m. Okay, why is that? Right. Okay, that's how we defined the, that's what this says. Okay, there's 1 over m, or the IE I have up there. Okay, it's 1 over m if you picked it randomly. Okay, chance of a collision, okay, is 1 over m. Okay, and so the expected number, that's the probability that I have a collision. So the expected number of collisions, well, the probability of the expected number is just, for an indicator random variable, is just the probability that it's 1. Okay, remember that basic fact about indicator random variables. Okay, and so that's one thing we're going to note. And the other thing is that c sub x is equal to, how can I express c sub x in terms of the cxy? Somebody give me a formula? Sure. Summation of all y in the table of little cxy? Not quite. Okay. So the reason is because I don't want to count a collision of x with itself. Okay. So let's subtract x from this. And now it's right. Okay? Minor technicality. Okay, if you got that wrong, you wouldn't lose more than 90% of the points. Okay, yeah?
Is there a relationship between the n in your universal set of hash functions and the number of slots in the table?
They're the same. They're the same. Identical. Okay? So you got to have the universal hash functions for hashing into your table. Otherwise, if it were larger, you would be hashing outside the table. Okay? Yep. Okay. Okay, so let's, now the math is pretty much just manipulation. So I take expectations of both sides, and I get the expectation of c sub x is the expectation of the sum of y in t minus x c x y. And that's equal to Somebody want to do the next step for me? One step. Just one step. Spread the wealth. Okay, somebody over here. Latecomers. Spread the wealth. What's the next step here? One step. Excuse me? Pull out the summation. Why am I allowed to pull out the summation? Very good. Okay, linearity of expectation. So we now have the sum of y in t minus x of expectation of cxy. Okay, next step. Okay, the steps get easier. Sort of like, duh, yeah.
We already know what the expectation of CXY is.
What is it?
1 over m.
Y t minus x, 1 over m. Okay? And so what's that equal to? Sure, fire away. N minus 1 over m. And that's less than alpha, which is what we needed to show, or n over m. Okay? So universal hash functions are great because the expected number of things per slot that I'm going to get, no matter how that somebody has picked the set of input keys, the expected number of things I'm going to get is going to be the average, okay, which is really nice. Yeah?
How practical is it to actually generate m hash functions if you're, I mean, most tables...
Well, you need more than m hash functions, right? Because the number of hash functions is the size of h, right? So generally, h is going to be much bigger than m. And in fact, who knows whether these things actually exist, right? Okay, a great definition. In fact, you know, there's a famous math thesis where somebody proved all these wonderful properties of this particular group, algebraic group. And it turned out, after he was granted his PhD, it was discovered that the group didn't exist, and that's why it had all these properties. Okay, because the empty set, you know, and so forth, have lots of interesting properties. Okay, can prove lots of properties, and so yeah, great property. Okay, just doesn't exist. That's why you can. Okay, but these do exist. So let's construct one. Yeah, so let's construct one. So there are actually different ways to construct them. Most of them are fairly similar, and they involve a bit of number theory. So we're going to have to learn a little number theory as we go through this. But it's not hard number theory. And most of it is sort of intuitive, and some of it you'll see. So it's modular arithmetic, okay, is what we're going to have to learn about. So constructing a universal hash function. Okay, I mean, it's amazing that these things actually exist, right? I mean, this is just, I think this is great stuff, okay? Just, it's great stuff, okay? You know, randomness is your friend, okay? It's interesting because I built, when I was, one of the times I took a stint in industry about, 12, 13 years ago, I worked for a company that was building supercomputers. And one of the things that I put into their interconnection network, which I designed and helped to build, was a randomized routing algorithm, okay, where you would route, the path you would take would be random. And what that would do is it would make it so that you didn't have the chance that there would be some pattern to route which would all congest in one place, okay? And when I told that, first of all, the hardware people were like, ugh. I said, well, look, it's pseudo-random, so don't worry, okay? And I said, ugh. So that, you know, finally I showed them all the advantages, and we did simulations, and okay, they were convinced, we built it, okay? So then we go, eventually it gets to the point where we're selling this product, okay? And this was at the time the largest computer, fastest computer you could buy in the world, okay? And you know, we went to the sales guy, and he said, now, you know, I got to sell this thing, so tell me a little bit. And I said, well, you know, it's a it uses this randomized routing algorithm. And so he looks at me with a state of shock, okay, and he says, you mean it doesn't always work? Okay. I said, no, it always works, okay, it's just that with high probability, it goes fast. And he says, you mean it could go really slow? Okay, he's thinking about how he's going to talk to a customer, okay? And I said, no, but the probability that's going to be really slow is so small, it's sort of like, the behavior of a gas. And he looks at me with this look of like, you really expect me to sell this thing? Okay. So then I said, don't tell the customers that. Tell them it has automatic load balancing. And he just brightened up, okay? And that he could sell, okay? That he could sell. But selling them randomness, no. People, randomness means I don't know what to expect, Okay, so we may get used to it. And in fact, now that has become a quite conventional thing to do, is to use randomness in your hardware. But at the time, it was, sort of very new stuff. Even now, you'll find a lot of people as soon as it's probability, they don't understand it, so they sort of, that's right. So this is the difference between good programmers and excellent programmers, okay, is this kind of knowledge, okay, that you can go in, or hardware designers. Okay, so let's construct this thing. So let's let M be prime. Okay? So we're going to only use prime sizes of tables for this. Okay? We're going to decompose a key k in U into r plus 1 digits. Okay? So the idea is we're going to write k as k0, k1, up to kr, where each ki is between 0 and m minus 1. Okay? So it's strictly less than m. So the idea is we have some big number, and you can sort of view it as what you do in base 10 when you take out the digits. That would be if m were 10. But we're going to do m a prime. Okay? So m might be 97 or something. We take out basically I can divide out by 97 repeatedly. I just convert to base 97, whatever the number is. Or if they're character strings, we can do the same kind of thing. Doesn't matter. Okay? So we decompose it into digits. Okay. Now is where we're going to have our randomized strategy. And this is what we're going to do is pick a set of values that are going to determine which hash function we use. Okay? So we're going to pick, with this randomized strategy, pick an A, which is A0, A1, up to AR, where each AI is drawn randomly. So when I say randomly without any other things, I mean, of course, uniformly. Right? I don't mean randomly where you randomly always pick key number 1, because your distribution is funny. Conventional meaning of this. So randomly from 0, 1 up to m minus 1. Okay? And now I'm going to define a hash function based on A of key k. And so this is going to be my set of hash functions, h sub a. So each h is a function of, it's going to be a function which depends on the random numbers that I've picked for the a. And in particular, it's going to be this value, sum I equals 0 to r of a I k I mod m. Okay? So that's going to be my hash function. So what is this? What is this thing here called? What am I doing to the two vectors a and k? How about somebody in this back corner? What am I doing to a and k when I form this sum? Okay, if I view A and K as vectors, what's this sum called? Are you calling me? Yeah. Dot product. Good. Good move. Okay, so this is actually just doing the dot product modulo M. Okay, just multiply component pieces, add them up, but you do it all mod M. Okay, good. So let's do one more thing I can squeeze on the bottom here. How big is H, which is going to be the set of H sub A's? How many hash functions have I created by this method? Yeah. R? How many different hash functions am I going to get?
M to the K.
M to the R. Not quite. M to the R plus 1. Good. Okay. So why is that? Well, how many choices do I have for A0? I'm picking them randomly from 0 to m minus 1. So there are m choices for A0. How many choices for A1? M. How many choices, etc.? How many choices for AR? M. How many numbers do I have here? R plus 1. So the number of different patterns I can get here, okay, is m times m times m times m, okay, r times. R plus 1 times, excuse me. Okay, so m to the r plus 1 different hash functions I've defined by this method. Okay, does everybody follow that? So that's base. This is 6042 material. Combinatorics, basic combinatorics. Okay? So everybody's, I hope, familiar with this. I want you to remember this. Okay? Actually, what we remember. Okay? Okay, we'll call this the Alamo. Okay? So we're going to remember it. Okay, so when I say remember the Alamo, that's the thing I want you to remember. Okay, because we're not going to get back to this for a page and a half. Okay? And we may have erased this by then. Okay? So, okay. So now, naturally, I want to prove a theorem. Okay? H is universal. Okay. In fact, let me just make a comment. This is actually a great hash function. This is a great hash function. Okay, because I mean, we're actually proving it's a good hash function here, but it's a great hash function. Okay, the only difficulty with this kind of hash function is this turns out to be a bit expensive to compute. Okay, because you're doing lots of multiplications and lots of modular operations which involve division. Okay, so it's a good method to use. It's just that it's can be very expensive to compute. Yeah.
I just have a question. So you take in two vectors, A and K.
Yeah.
And then you have the summation. So the result of that is just a single number.
Yes.
I'm just having trouble seeing how this maps. Shouldn't it map like each element of the vector K to a certain slot? Isn't that
Well, that's where the mod m comes in. So I get some number here. Then I take that number mod m. And what values do I get? 0. If I take any number mod m, it's going to give me a number between 0 and m minus 1. Okay?
Taking two vectors and you get a single number, though.
That's right. And then I take that, mod that, or I can mod as I go along, which is probably the preferable way to do it, just because you don't want the numbers to get too big, because then the multiplies Cost you even more. Okay? But yes, and so the end of it is this. And so notice, though, if I change any one of these values, the value of this calculation changes. Okay? So did you follow that? That it ends up, I mean, I should have checked that because that's important. This does map, one of the important things is that it maps things to the range 0 to m minus 1.
For some reason I would expect, like, if you take two vectors as input, like, you have the vector as output or something. That's what's confusing me. You know what I'm saying?
Well, a dot product is basically doing the, you can view it as multiplying, A times K transpose, right? So if you do that matrix, did I do this right? No, wrong way. A transpose times K. Okay. Okay, so we're multiplying that vector times that vector. So you take that row times that column, and that gives me my result. Okay, and that's a single value. Okay, and then whatever that value is, I take it mod K. Okay, so I take the pairwise elements, multiply them together, and add them all up. Okay, gives me a single number. Okay? I mean, that's what you're trying to do, is you're trying generally with hash functions to reduce to small stuff. So it makes sense to, to look at something like this. I mean, okay, let's prove this theorem. Any other questions? Yeah.
So how do we ever get back? So if I'm actually programming using this, how do I ever get back to what I stored in this key as my hash function for n?
Because you're going to store what the A's are. Okay, and so you can always recreate. You can always hash with the same thing. You store what so you pick at the beginning of your code, of your competition, you pick a bunch of these random values. Now, through your compiler competition, you use this set of values whenever you access the hash table. You're always using this value. Okay? This is only to pick the hash function out of the set of hash functions. Okay? So this is defining the set, and also when I pick one, I pick it by picking all the A values. Good question. Good question. Yeah?
I'm still just having a hard time visualizing what this does. I mean, so you have an element that you want to put into a hash table.
Yeah.
How is this related with K and A again?
Okay, so I have an element which is some key K. That's going to be the element that I want to hash. Okay, and we're going to break it into a vector. So for example, let's say it's a number. And let's say m is 10. Well, the way that I'll break it into a vector is just by considering it as I'll take digit by digit. Okay? But normally what I do is just convert it base m into its base m representation, and that'll give me those digits, each of which falls in the range from 0 to m minus 1. Each digit will fall in that range. So I take whatever the number is that represents the key, and then basically look at it as an as a base m number with r plus 1 digits. Yeah? You can add zeros. Yep. Yep, doesn't matter.
So then after you break it down into m digits, then you have
No, not m digits, into base m. So we have r plus 1 digits. Okay, because each digit is, so for example, if I take the number 2 to the 16th, say, and I write it in base 10, okay, so 10 is my m, I don't get 10 digits. I get only 5 digits. Is that right? Okay. I shouldn't have flinched there. I should have said, that's just 5 digits. And everybody would have said, oh, yeah, of course. He's the professor. He knows what he's talking about.
So you have r plus 1 digits, and then you're doing the summation. So when you're doing the summation itself, are you doing these multiplications within the summation?
So when I form this, I'm performing a multiplication here of each pairwise digit. So I take, let's do it. Let's take, suppose that my number is 3, 4, 8, 9. Okay, let's say it's base 10 that I'm doing. Okay, and I pick a random number for that's k. And I pick a random set of digits for this, and that might be 1, 0, 4, 2. Okay, for my a. Okay, and this is where we're all going to do base 10. Okay, so what I'll do is I'll do 3 times 1, 4 times 0, 8 times 4, 9 times 2. Okay, now I don't do 10 normally because 10 isn't prime. I have to do it prime. I'm just doing this for illustration. Okay, so that's 3, 0, 32, and 18. I add those up, and I get 1353, and I take that mod 10, and that equals 3. So therefore, this key under the function h sub a maps to 3. Okay, slot 3. Okay? Okay. I probably should have included that to begin with. That's a good example. Okay. So h is universal. So let's just using the definition of, let's break our 2 input keys that we're saying are distinct, okay, into their digits. Okay, and what am I trying to show? I'm trying to show that the number of hash functions on which these map to the same value, okay, is 1/mth of the total number of hash functions. And what's the total number of hash functions? Okay, it's the Alamo, right? Remember the Alamo. What's the Alamo? M to the r plus 1. Okay, so how many do I want this to? Okay, we want this to collide on exactly m to the r, if it's universal. Okay? Good. So these are distinct keys. Distinct digits. Distinct keys, sorry. Keys. Okay? These are distinct keys. So if they're distinct keys, could every one of these be the same value? No, because then they'd be the same number. Okay? So one place they have to differ, at least one place. Okay? Now we could do the math for any place, and it gets messy if I pick it in the middle because I have to sort of pick it out. So what I'm going to do is make it simpler by saying, let's assume it's x0 and y0 are the different ones. Okay? Because it wouldn't really matter which one was different. The math is just easier if the symbol manipulation is easier if I assume that it's position 0. So they differ in at least one digit, and without loss of generality, W log. Some people say that's with loss of generality, but it's supposed to be without loss of generality. Okay? Position 0. Okay, so for how many, we want to count up for how many h sub a in h, okay, do x and y collide. This is why I said to you folks, wasn't it good you showed up to class today? Okay, because you know, the interaction for this sort of class can be critical for how much work you have to do to understand what's going on here. Okay. Okay, so for how many h sub a do x and y collide? Okay. So if they collide, that means that we must have that h sub a of x equals h sub a of y. Okay? And so let's just write that out in terms of the definition of h sub a. Okay, so if that's the case, that implies that the sum from I equals 0 to r of ai xi must be congruent to the sum of I equals 0 to r of a sub I yi when we take it all mod m. Okay. So when I calculate these out, so everybody knows this, does people familiar with this notation for modular? stuff, yeah? Okay, is this from high school? Is this from, where do we teach this? 042? Okay. 001? Okay, good. So you've seen it somewhere. Okay, good. Okay. So, and this is just applying the definition. So I could say summation of ai xi mod m if I want to look at mod as an operator. But for this, it's going to be convenient just to view it as incongruence as mod m, because it's simpler to manipulate the formulas than getting the mod stuck in there all over the place. Okay, so that implies that the sum of I equals 0 to r of ai times xi minus yi is congruent to 0 mod m. Okay, so what did I do? Yeah, just threw this over, used the distributive law. Okay, threw that over, subtract it from both sides. So that implies that a0 x0 minus y0 plus summation of r equals 1 to r of ai xi minus yi is congruent to 0 mod m. Why is that true? New hands, new hands, new hands. Okay, you win.
Just change the indexing from I equals 0 to R equals 1.
Yeah, good. Just pulled the 0 term out of this. Split the summation. 0 term plus the rest of the summation. Okay? So that means that a0 times x0 minus y0 is congruent to minus the summation of r equals 1 to r of ai of xi minus yi mod m. Okay? How did I do that? I equals 1. Okay, yes. You're supposed to say, you shouldn't say, should that be I equals 1. You should say, that should be I equals 1. That shows some confidence, self-confidence, okay? Okay. Now, for the next step, we're going to use a fact from number theory. So let's pull out our number theory facts before we continue on. So just hold that part of the proof. You can box this so that you know to go around it when we actually continue that. We're going to continue that in a minute, but we're going to use the following number theory fact. And this is all in the book, by the way. If you want to look this stuff up, there's a chapter on number theory that we're not going to be covering, but which is helpful sometimes for understanding these things. So let m be prime. Then for any element z in z sub m, so what is this? Does people know this notation? Okay. This is the set of integers mod m. We usually represent them as just the least positive or non-negative numbers 0 to m minus 1. So that if I have m, I just think of it as 0. If I have m plus 1, I think of it as 1, and so forth. Okay, so I look at all the integers, but I really am just looking at the integers and just doing modular arithmetic. So for any z in z sub m, the integers mod m, okay, such that z is not equal to 0, okay, so it's not a multiple of m, okay, it's if you want to look at all the integers, but if I'm looking just at the elements of zm, it's not the 0 element, okay. There exists a unique z minus 1, okay, in zm, such that z times z minus 1 is congruent to 1 mod m. Okay, so what this says is that for any value that I take, so let's do an example here so people understand what this theorem is, this fact is saying. Okay, so if m is 7, I can make a table here of z and z inverse. Okay, so what is the inverse of 1? 1, okay, because 1 times 1 is congruent to 1. What's the inverse of 2? 4, because 2 times 4 is 8, mod 7 is 1. Okay, what's the inverse of 3? 5. Okay, 3 times 5 is 15, mod 7 is 1. Okay, 4, 2, because the same reason here, 5, 3, and 6, 6. Okay, so notice that there's a unique one. Okay, every one has a unique inverse. Okay, and that's going to let me do, and that's all this says, that there's a unique inverse. Okay, there's something which will cancel that out. So if I have that as I have here, what I'm going to want to do is I know this isn't 0. I'm going to try to solve this for a0. And I can do that by canceling it out on this side and putting the inverse over here. Okay? Because normally, I can't, if m isn't prime, I can't do that. Okay? If m isn't prime, I can't do that because there can be numbers, two numbers that, there can be numbers that if I canceled it, I get the wrong thing. Okay, so let's see. So since, this is back to the proof over there, since x0 is not equal to y0, we know that this x0 minus y0 inverse exists. So therefore, I can cancel it from the left there, just as I just said, okay, and solve on the right, and I get that a0 is therefore congruent to minus summation I equals 1 to r of ai xi minus yi times x0 minus y0 to the minus 1, whatever this element happens to be. Okay. Now we make an argument. Okay? So what is this saying? It says, what have we just shown here? It says that if we have hi collide with, ha of x collide with ha of y, okay, then a0, or whatever the index would be, you notice it would get messier if I said the index were some index k or something, because then I got to write, I can't do the continuous, I got to write two summations everywhere and stuff. So if it says that a0 can therefore be expressed as a function of the other x's and the ai's. Okay? So, so what I want to, so let me just write that down. Thus, for any choices of a1, a2, ar, exactly one of the m choices for a0 causes x and y to collide. Okay, however I pick the, okay, so consequently the number of HAs that cause x and y to collide is equal to, well, how many choices do I have for A1? I have m choices for A1. Okay, so this is choices for A1. And how many choices do I have for A2? M. Okay. And how many choices for AR? M. And then the fast thing I'm going to do is pick A0. How many choices do I have for A0? I have only one choice for A0 if they're going to collide. What's the choice that I make for A0? That one. Okay, that one. Okay, but I have only one choice. Okay. And so what's that equal to? M to the R. And that, if you remember the Alamo, is just H over M. QED. Hard proof. Okay? Take a little study to get your head around it. Okay, hard proof. Okay? Hard proof. Okay. Now, a really fun topic. Perfect hashing. Haven't taught this in this class before. Okay, previously I thought this was graduate material. But it's not, I discovered. So we'll talk about perfect hashing. It's got a great title, right? We're all interested in perfection, right? Okay. Here's the problem. We're given n keys. We want to construct a static hash table of size m equal order n. Okay. So small hash table, not much bigger than the keys themselves, such that search takes theta 1 time in the worst case. Okay? Have a set of keys. I want to be able to look any key up, whether it's in hash table, constant time. Worst case. No expectation or anything. Okay? Just boom, go and get it. What's fun about this topic is, although we're going to come up with a hash table that can do it, our construction of the hash table is going to be randomized. Okay? And so what we're going to do is we're going to say, okay, we're going to get some probability that this construction produces a hash table with the property that we want. And then all we have to do is try it out on a few things, and very quickly we'll find one that it works on. And that's how we build it. So the construction of this is not going to be linear time. It's actually quite close to linear time, actually. Okay, it's linear, I think, expected time. Have to think about that a little bit. I didn't think about that one. Ooh, that's a good problem for. Okay, the quiz isn't. We still have a week on the quiz. Okay. Okay, so this is pretty remarkable, right? Somehow we're going to. The basic idea is going to be to use a two-level scheme. With universal hashing on both levels. So we're going to have a two-level hash table, and it's going to look something like this. Let me see. I think I'll make a bigger table here. a little bit. Okay. Here's my hashtag. This is such a cute scheme. This is just gorgeous stuff. Okay. So here we have a table, T. Okay. That's our first level. We're going to have some slots in that, and in each slot, we're basically going to use an idea like chaining. Okay. But what we do when we get to a slot is rather than chaining things, we're going to have another table. Okay. And then we're going to hash in that. And in the second table, we're going to guarantee no collisions. So here we might have collisions. Second table, no collisions. Okay? Because we just take all the elements that collide at level 1, and we make it so that with a second hash function, we can do that. So the way that we're going to store this, let's say this is slot number 1 and this is slot number 6. What we're going to do is we're going to store the size of the table at the next level. It's called m sub I. Okay? So let's say this is 4. So this is going to have 4 elements in it. Okay? And we're also going to store the A. Let me just call it M and A. I think that's the A for the table. Okay? Whatever we're using for our universal hash function on this table. Okay? Now here I've actually used, as you'll see, square numbers, and you can modify this. The book has a more technically accurate way. So this is going to be my A. Let's say it's a 2-digit A. Okay? 31. And then I've got a pointer to the table. And this is where I'll store my keys. In this case, I'll have, say, 14 and 27 stored there. And this is my table S1. And these are both nil. And down here, maybe, I have a table of size 9 with a hash with a value 86 for generating my hash function. And it points off to a table of size 9. Okay, 1, 2, 3. Okay. And so this would be, say, S6. In this case, it's got just 3 values stored in it. And I say the key thing we're going to do is we're going to have no collisions at level 2. Okay? That deserves an exclamation point, because 2 factorial is equal to 2. Okay. No collisions at level 2. You don't like my math jokes? Okay. So this is going to be very sparse at level 2. Okay. So how are we going to do this? So most of the analysis of this is the analysis of level 2, because once we have level 2 analyzed, level 1 we understand already. Why do we understand level 1? Well, this is just the same analysis as hashing with chaining to do the level 1 analysis, right? How many things fall into each bin? Okay. We'll see, actually, it's going to be a little bit more interesting than that. Okay, so level 2 analysis. Okay. So the number of slots we're going to pick to hash the keys in at any given level, okay, we're going to pick as the square of the number of things that we're putting in there. So what we're going to do is prove the following theorem, that if we hash n keys, okay, into m equals n squared slots using a random h in a universal set script h, that implies that the expected number of collisions we'll get in the table is less than 1/2. Okay, so we don't expect to get many. In some sense, this is the opposite of the birthday paradox. Okay, so you remember the birthday paradox says that, you know, if I take somewhere around square root of the number of people in a room, okay, sorry, if I have 365 birthdays, it actually says, to get all the constants right, if you have 365 birthdays and you have people who are drawn, all it takes is around 22 people to have an expectation of one of them, of a pair of them having the birthday. Okay? Doesn't take something that's really close to 365, and the reason is because there are that many things that have to be avoided when you look at the pairwise interactions. This is sort of the opposite of that. It's sort of at about the same place, which turns out to be about the square root of the number of slots. Okay, as long as you have less than that, okay, or equal to that, then the number of collisions you expect is at most a half. Okay, that's what we're going to prove. Okay, so what's going to happen is at this level, we're going to use quadratic space, but it's going to be okay when we add it all up. Okay? It's going to be okay when we add it all up, even though we're using quadratic space for each slot. Okay? So let's prove this. Okay? So the probability that two given keys collide under H is what? 1 over m. That's definition of, and that's equal to, right, 1 over n squared. Okay? 1 over m, 1 over n squared. Okay? There are how many pairs of keys? Okay, right? This is, yeah.
N squared plus n squared minus
N choose 2. Good. We'll get there. Okay, there are n choose 2 pairs of keys. Just pick the pairs of keys out of n. What you were doing is jumping ahead a couple steps. Okay? So that implies the expected number of collisions, okay, is, and this is going to use what property we're going to use actually to do this. So I'm cutting out a few steps here. So I'm cutting out linearity of expectation here. Okay, so the probability of each one occurring is 1 over n squared. And there n choose 2 of them doing it. So the total expectation is just the product of those. Okay, by linearity of expectation. And that's equal to n times n minus 1 over 2 times 1 over n squared. Okay. And, well, this is n squared minus n. This is n squared. So therefore, this is all less than what's left over there, which is 1/2, which is what I wanted to prove. Fairly simple argument. Okay. So we're almost done here with this analysis for perfect hashing. It's really quite remarkable it works as well as it does. Okay. So, corollary to this is that the probability that there are no collisions is at least 1/2. Okay? So I have some probability that there's no collisions. Okay, I'm going to get that from the expectation. Does anybody remember the simplest law that goes between probability and expectation? Somebody's inequality? Okay. Markov's inequality? Okay, please review. Okay, things like this are on the quiz. Okay, so this is for a random variable x which is greater than or equal to 0. And it says that the probability that x is greater than or equal to t is at most the expectation of x over t. That's what Markov's inequality says. And you should be able to prove this from basic, even if you've never seen this. This is a 5-minute proof for somebody who's done 6042, okay, or has had basic probability, okay? Just definition of expectation, okay? So the probability of at least one collision, okay, in our case, is going to be less than or equal to the expectation of the number of collisions over, what's the formula for the denominator here? One. Okay, just plug in t equals 1. Okay, well, we computed the expectation of the number of collisions. Okay, so that's less than a half. Okay, so that's the probability of having at least one collision. So what's the probability of having no collisions? At most, a half. So we're done. Okay, so to find a good level 2 hash function, all we have to do is test a few. Each one we test with the new random numbers gives us a probability of 1/2 of it being one where there'll be no collisions. Just hash the things in. If they collide, pick another random one and try it again. Okay? And we may have to go a few times, but very quickly the probability will become infinitesimally small that I didn't find one that worked. And I know they're out there because the probability is greater than 1 of this happening. Okay, it only remains for us to analyze the storage of this scheme. Okay? Only remains to analyze the storage, because we've now said we can always find with n squared, we can always, with probability of half, we can find such a table. Okay? So this is actually a very famous, a variant on a very famous type of argument that was popularized by the mathematician Paul Erdős. Okay, using what he calls the probabilistic method, where that you prove that the probability of something existing is greater than 0, and then he can conclude that such a thing must exist. Okay, and this is a variant on that type of argument. Okay, very famous, and so the analysis of storage is really simple because we've done it before. Okay, so for level 1, okay, we're going to choose m equals n. And let's let n sub I be the random variable for the number of keys that hash to slot I in T. Okay? And we're going to therefore, on its level 2, we're going to use n sub I squared slots for each level 2 table S sub I. Okay, so we use the square of the number of things that hash to it. Okay, so the top level is just like chaining, except now instead of chaining, we're going to put them in this smaller hash table. It's now going to have quadratic size. So to skip over a few steps, which I think at this point I have a right to, the expected total amount of storage is just the expectation of the sum of I equals 0 to m minus 1 of something proportional to n sub I squared. Okay, just add up the squares of everything that falls into each bin. That's all I'm doing. And then we do it with the total storage is this, and we just take expectations of both sides. Now, What's this? Who went to recitation last Friday? Ah. What did you analyze in recitation? What?
That the expected value of the number of elements in each slot is 2 of the units each four.
Okay, but what did you analyze in? That wasn't my question. That's once again, you skip ahead a lot. Got to slow down, because you go too fast for me. Okay, so my question was, what did you study in recitation on Friday? Boy, it's so long ago. Bucket sort. And you analyzed the running time of bucket sort when you use insertion sort. And remember that basically, you were adding up the cost of searching, okay, in each of the, of inserting into the sorted list at each level of bucket sort. So it's exactly the same thing. And what did you discover the running time of bucket sort was? Order n. Okay? Okay, the analysis is identical to bucket sort. Okay? Identical. It's exactly the analysis we did before in bucket sort. Okay? And if you want to get a probability bound, which you can get so that you can say, in fact, that there is one whose total storage is n, so it's not just the expected, once again, you can use the Markov bound, and that's where you were headed. Okay, so that you can say, if I use at least 4n, okay, and actually that's done in the book, and I'll let you look at that. So you can get a Markov bound to guarantee that you have it. So we've constructed this two-level hash table randomly, and the hash table we end up with has the property that its worst-case time, there's no expectation or probability or anything left once we've constructed it. Once we've constructed it, it has the property that lookup is order 1, okay, in the worst case. Okay, but we may have to try a few attempts to find a hash table that will work for us, okay, at the various levels and so forth. But once we do that, it's guaranteed to work in order 1 worst case. Question?
We're going to use order n storage anyways. Why don't we just use an array and correct address number?
Because for the same reason we normally use it is that the range of keys may be so huge. Suppose there's 64-bit keys that I want to store. Okay, way too big. So this is basically giving you all the advantage of direct access. Now it takes 2 levels of addressing, and it takes 2 applications of hash functions. Okay, you hash to it, you then look up what the hash function is that you need to do, and then you index into the array. And also I cheated here because here I use square numbers, and in fact you can't do that for the universal hash function I presented, but that's a technicality, and the book does deal with it properly. Okay, I made that so that this would be a simpler presentation. Okay, really cool stuff. Okay, you can build a table that lookup of any character strings or whatever, constant time. Good stuff. Okay, good luck on the quiz next week.